Lesson 13, Fourier series. Section 13.2, Principle of Superposition. Let me show you how a square wave is synthesized using trigonometric functions. This is a sine function. The amplitude is Vm, and the frequency is f. We call these parameters fundamental amplitude and fundamental frequency respectively. This is another sine function. The frequency is 3 times higher than the fundamental frequency. We call this the third harmonic function, and the frequency the third harmonic frequency. The amplitude of this third harmonic function is 1/3 of the fundamental amplitude. This waveform is the sum of V1 and V3. The frequency of this sine function is 5 times higher than the fundamental frequency. We call this the fifth harmonic function. This waveform is the sum of V1, V3, and V5. It resembles a square function. This is the seventh harmonic function. The summed waveform becomes closer to a square wave. The sum of up to the 35th harmonic function looks very close to a square wave. If you add an infinite number of harmonics, then the synthesized waveform becomes a square function. Let me show you another example. This is a fundamental function. This is the third harmonic function. Its amplitude is 1/3 squared and its phase angle at t equals 0 is 180 degrees. Then the sum of V1 and V3 looks like a triangle wave. This is the sum of up to the 35th harmonic, and it is almost a triangle wave. We have seen that a square wave and a triangle wave are sums of trigonometric functions. Next, let's see how the AC analysis methods are applied to these non-sinusoidal periodic wave forms. The key idea is the principle of superposition. When a square voltage is given, we replace it with a fundamental voltage V1, and its harmonic voltages V3, V5, and so on. We can apply the AC circuit analysis methods to each case where a sinusoidal voltage is separately applied to the RC circuit. We calculate the responses Vc1, Vc3, Vc5, for the source voltages V1, V3, V5. Then we can superimpose the individual responses. The sum is the total response Vc1 plus Vc3 plus Vc infinity. From top to bottom, let me explain the calculation procedure step by step using equations. The source voltage V is given as a square wave. It can be expressed as a sum of trigonometric functions. The harmonic component Vk is expressed by this sine function. Uppercase Vk is the corresponding complex number. It is applied to the RC series circuit, which has the capacitive reactance negative J times 1/k omega c. Then Vck is obtained by using AC circuit analysis methods. It is converted into a trigonometric function lowercase Vck. We superimpose all the harmonic components to obtain the total response. Note that, if the frequencies are different, the complex numbers cannot be superimposed. Because, in the conversion process to the complex number uppercase Vk, the frequency information is lost. We can superimpose the time-varying variables. Because, during the inversion process to the time-varying variable lowercase Vk, the frequency is restored. Exercise 13.2.1. The source voltage is a non-sinusoidal periodic voltage that can be expressed as V equals V1 plus V3. V1 is the fundamental voltage, and V3 is the third harmonic voltage. The fundamental frequency F equals 15.9 kHz. Calculate the capacitance voltages Vc1 and Vc3, by applying V1 and V3 separately to the RC circuit. Note that, uppercase VCK and uppercase VK are complex numbers. Calculate lowercase vc1 and vc3. Here, lowercase vck is a trigonometric function. Draw the waveform of Vc, which is equal to Vc1 plus Vc3. The answer to exercise 13.2.1. When the source voltage is V1, then the capacitive reactance is found to be negative J kilo ohms. Vc1 is calculated as negative J over 1 minus J times Ve. Thus lowercase Vc1 is obtained as Ve sine omega t minus pi over 4. When the source voltage is the third harmonic voltage V3, the capacitive reactance is 1/3 of the reactance at the fundamental frequency. Uppercase Vc3 and lowercase vc3 are calculated as shown in these equations. This is the waveform of Vc. This is for your reference. If harmonics up to 999th are summed, the source voltage V becomes almost a square wave, and the capacitance voltage Vc becomes very similar to the experimental result. Exercise 13.2.2, this is your homework. Pause the video, and write the answers. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.